Today we will be discussing the program for the division having the 16-bit dividend. So the difference is very simple, that this time the dividend is of 16-bit and divisor is of 8-bit. And with these two values, we have to write the program for the division. So as far as the flowchart is concerned, there will be no change at all. But the program will be changed because this time the dividend is big. It is a 16-bit number and the divisor is an 8-bit number. So you might be knowing the meaning of dividend and the divisor. Dividend is that which is to be divided. Dividend is the number which is to be divided, and divisor is the number which is going to divide. So this time the dividend is long, so it will take more time to execute and find out the result. And one more thing is also very important, that whenever you are going to divide two numbers, dividend from the divisor, it may be possible that you will be getting two results. One is called quotient and another is called remainder. So both of these values have to be stored in the form of a result. So that is why first we will discuss about the flowchart, how the flowchart will work for division, 16-bit division, if the dividend is 16-bit and the divisor is 8-bit. So first of all, we have to know that what is the value of the dividend, as well as you have to know that what is the value of divisor, as well as we have to initialize the quotient. Quotient value has to be initialized because in the very beginning quotient will be 0. So the number of times the divisor is going to divide the dividend, the number of times it is going to divide the dividend, it is called the quotient. And when the value of the dividend become less than the divisor, the value which you will be getting, it will be it is called as a remainder. For example, if we have to divide 4 by 3, so whenever we are going to divide 4 by 3, it will go one time. It means quotient value will be 1. But when the quotient value will be 1 and 4 minus 3, you will be getting 1. So the next dividend value is 1, which is less than divisor, that is 3. So 1 cannot be divided by 3. So if 1 cannot be divided by 3, so 1 will be the remainder. So it means in case of division, we have two values in the form of a result. One is remainder and another is the quotient. So whatever we are left in the last, whatever we are left as a dividend, which is less than the divisor, is known as remainder. So after initializing the value of the dividend in a 16-bit register, as well as initializing the value of the divisor in an 8-bit register, considering any register to store the quotient value, and the number of times it is going to divide, the quotient value will be increased. So initially it is 0, 0. And since we don't have any instruction to make the division, so what we are going to do, we are going to subtract the dividend. We are going to subtract divisor from the dividend, and the resultant is known as dividend. And after doing many operations, you have to check the dividend has become less than divisor. And meanwhile, we have to increase the quotient value. So as the number of times dividend is more than the divisor, we are going to subtract divisor from the dividend and increasing the quotient value one by one till the dividend become less than the divisor. When the dividend will become less than the divisor, what we will obtain, the remainder, that whatever dividend is left, it is known as remainder. And then we have to store the quotient value as well as the remainder value into the end. So this is the flow chart. If the dividend value is 16-bit and the divisor value is of 8-bit, then what? Then the program. So uh, so we will be discussing the program for the 16-bit division. The dividend is of 16-bit and the divisor is of 8-bit. So first of all, we will be considering that what is the value of the dividend. Dividend is of 16-bit and divisor is of 8-bit. Putting quotient value as 0, 0, and then subtracting the divisor from the dividend, increasing the quotient value by 1, and checking whether the dividend has become less than the divisor or not. If the dividend has become less, is not less than divisor, we continue this process of this loop in which dividend is again divided, subtracted with divisor, and then quotient value. So the time till the dividend is more than the divisor, you are able to find out the dividend is more than the divisor. Then you are going to make this process dividend minus divisor. And meanwhile, you will also going to increase the quotient value. And then you are going to check whether the dividend is less than the divisor or not. If the dividend has become less than the divisor because dividend is subsequently subtracted with the divisor, and the time will come when the dividend will become less. So when the dividend will become less, we will come out of this loop, and whatever is the dividend, that will be called as a remainder. So this is the flow chart of the division program. So let us now discuss the program. So first of all, since the dividend is of 16-bit, and suppose that 16-bit number is available at 8500 and 8501. So 8500 and 8501 contains a 16-bit number individually, 8-bit, 8-bit. And so what we are going to do, we are going to admit, we are going to store, we are going to load the content of 8500 in L register and 8501 in H register. So HL pair now contains the 16-bit dividend, which is available at 8500 and 8501. Then 8502 is the memory location where the divisor is placed. So we are going to load the divisor value into the accumulator. So it means dividend is placed in HL pair and the divisor is placed in accumulator. So with respect to this particular flow chart, the first unit of the flow chart, LHLD 8500 is going to load HL pair by a 16-bit dividend. And with the help of LDA 8502, we are able to store an 8-bit number into the accumulator, which is actually the divisor. And then we have to take the quotient also, but meanwhile, what we have to do, once we store the divisor value into the accumulator, for the safety point of view, we store it into the register. Suppose C register is used for that particular purpose. And then we have to take the quotient. Suppose the quotient, and for the quotient, we are taking D pair to store the quotient. And since it has to be initialized, so that is why 0000 is placed in the D pair. And this D pair will be giving you the information about the quotient. So now what we will going to do, now HL pair contains the dividend. The dividend is of 16-bit. Lower order is stored in L register and higher order is stored in H register. So whenever we start subtraction, we will first load the lower order content, that is L register content, into the accumulator, because we have to do the dividend. We have to subtract the divisor from the dividend. So the lower part of the dividend is stored in accumulator, and then we are going to subtract the value of C register. Now C register contains the divisor value, because 8502 is containing the divisor. It is stored in accumulator and later on it is copied in the C register. So we are going to subtract C. So it means what we are going to do, we are going to subtract the divisor value from the dividend, not the 16-bit, but the 8-bit of the lower order 8-bit of the 16-bit dividend. So once we are going to subtract this value of C, the accumulator content will be modified, and an accumulator content will be L minus C, means whatever is the content of the L register, which is the lower order dividend, which is placed in accumulator. Now it is being subtracted from C. C is subtracted from accumulator. So naturally, and the result will be stored in accumulator. So naturally, after the subtraction, the accumulator will contain the lower order value. Now, this result, which has been obtained by subtracting the content of C, which is the divisor, from the content of accumulator, which is actually the lower order content of dividend, while subtracting, accumulator will change. And when the accumulator will change, this accumulator value will be the partial result, and that result will be stored in the L register. Now it may be possible that whenever we are doing subtraction, subtracting C from accumulator, it may be possible that the accumulator content will be more than the content of C. If it is so, carry will not be generated. But if it is not so, carry will be generated. So if carry is not generated, we will skip. If the carry is not 1, it means the accumulator content is 1. It is more than the divisor, means the dividend content is more than the divisor. So if it is not so, it will jump on no carry, and it will jump on no carry. Where it will jump? It will jump to the skip. What is a skip? We will discuss it later on. But if there is carry, if carry is generated, if it means the content of the lower order dividend is less than the content of the divisor, then in that case, what we have to do? We have to take the borrow. We have to decrease the value of H register content. So that is why if carry is generated, it will decrement the content of H, because we have to subtract the borrow from the previous value. Because whenever we are subtracting C, it will give some result in the accumulator, whether the content of A is less than C or content of A is greater than C. If the content of A is greater than C, then no problem. Then we have not to decrease the value of H. But if the content of accumulator is small than the content of the divisor C, then we have to decrement the value of the H. Since we cannot do 16-bit subtraction from the 8-bit, that is why we have to do this process. And what is a skip? Skip is that if there is no carry, it means the content of accumulator is more than the content of C. It means the content of lower order dividend is more than the content of the divisor, which is C. Then we have not to decrease the value of H. And then what we have to do? We have to increase the quotient, because one time the division has been, subtraction has been done. So we will increment the quotient. So quotient is equal to quotient plus 1. So we will increment the quotient. Now, since we have, if it is possible that carry has been generated and the H value has been decremented, so it may be possible that the content of H register may become zero. It may become less. So first of all, what we'll do, we have to check it. And for checking it, we have to copy the content of H register into the accumulator. Once we copy the content of H register into the accumulator, then what we'll do, we are going to check whether it has become zero or not. If it has become zero, then the zero flag will be set. And if it has not become zero, suppose it is previously 0.3. So if it is being reduced here, it will become 0.2. So in that case, the CPI 00 is not going to set the zero flag. So if it is not zero, it will go back and it will copy the content of L into A, because we have already copied the partial result into the L. So that L will be copied in A. But if the zero flag is going to set, what we are going to check whether we are going to copy the content of L register into the accumulator, and we are going to check whether this content of lower order which is placed in accumulator has become less than the dividend. It means both this process of checking of H as well as L is going to check whether the dividend has become less than divisor or not. And if it is not so, it will go to back. So in both the cases, if H is not equal to 0 as well as L is not less than C, in both the cases, it will go back and it will do the subtraction process. So let me discuss once again. So first of all, content of lower order dividend is copied in accumulator. Then C is subtracted, which is the divisor, is subtracted from accumulator. And whatever is the partial result, it is stored in the L register. And since carry has not been generated, so we will not decrement H. So we will go here and increment the quotient value. So quotient value now it will become 1. And now we are going to check whether the H has become 0 or not. For that, we have used this one. If it is not so, it will go back. If it is not 0, it will go back. But if the process, it may be possible that while decrementing H will become 0. And the time when H will become 0, it will provide the value. Because what happens that the L register and H register contains the lower order and the higher order respectively. When the lower order content is less than the divisor, then it has to take the borrow from the H register. And in this process, it is going to decrement the value of H register. And then in this process, it may be possible that the H register content will be reduced. And the time will come when the H register content will become 0 after few loop process. And the time when it will become 0, it will come over here. So it may be possible that when the H content will become 0, it is not necessary that L content is also 0 or less than the divisor value. So what we are going to do, that's why we are going to load the content of L register into the accumulator and then comparing it with the C to check whether the lower order is also is less than divisor or not. If it is not so, it will go back and it will copy the content of L register into A and it will do this process. So the number of times it is going to do the looping process, it is going to subtract the value of the divisor from the dividend, as well as going to increment the value of the quotient. And when the time will come, a time will come when the value of L register and H register individually, both H register will become 0 and the L register will become less than the divisor. At that time, we will skip. So whenever we are skipping, we have to store the value of result, that is the quotient, as well as we have to store the result of remainder into the memory location. Suppose 8602 has been assigned to store the. So what it is going to do, it is going to store the content of HL pair into the 8602. So it means it is going to store the content of HL pair, and HL pair contains what? HL pair contains the value of the remainder, because the remainder value will always be less than the divisor value. H will contain 0, 0 naturally, and L will contain that value which is less than the. So whatever is the content of HL pair, that will be considered as a remainder value. So we are going to store the content of HL pair into 8602 and 8603. So 8602 will contain the content of L register, and 8603 will contain the content of H register. Now we have also to store the value of the dividend. Dividend is stored in D pair. So what we are going to do, we are going to exchange. Now exchange is an instruction which has been discussed earlier also, to exchange the value of D pair with the HL pair. So D pair contains the what value? D pair contains the quotient value. So that quotient value will be exchanged with the HL pair. Now HL pair contains the quotient value. Now we will store the HL pair content into 8600. So HL pair is now having the dividend. So lower order of that DE register, which is stored in L, it will be placed at 8601, and H register content will be placed in 86000 and 01. And then it is going to halt. So in this way, this 16-bit division can be obtained from with the help of 8-bit divisor. Of course, we have to do some processing in between, because the time will come when the value of the lower order dividend will become less than the value of the divisor, and it has to take the borrow. And in that process, the content of the H register, that is the higher order dividend, will have to be reduced, and the time will come when the content of higher order register will become 0, even though it may be possible that the content of L, which is the lower order dividend, will not be less than C. So what will happen? The C will be subtracted from L until the value of L will become less than the C. And this is going to do all this process. So this is the program which is used for division 8, where dividend is of 16-bit and divisor is of 8-bit.
Yes, sir.
Okay, now going to start the next program, which is BCD to binary conversion. Now, what is the meaning of BCD to binary conversion? What is the importance of BCD number, and why it is required to convert the BCD number into the binary number? Now you have seen that most of the appliances, most of the products which is based on microprocessor, normally the data which are required to be entered into that microprocessor based system, or the display of that microprocessor based system, is used to be done in decimal number. If you take an example, that if you see in the laboratory, the instrumentation instruments which are used to measure the current and the voltage, these voltage and the currents are represented in decimal number. And also the data which is used to insert, which is entered into this product, it is also through the decimal keyboard. So the monitor program which is stored in that microprocessor based system, it is going to convert each key whenever it is being pressed in the form of from the decimal keyboard. It is going to convert each key into equivalent 4-bit binary number. Whenever we press 7, so what will happen? The corresponding binary number will be stored in the corresponding to the 7. Similarly, when we press 8, so binary number corresponding to 8 in the form of a 4-bit is being stored. So what is done? That particular program, whenever we are going to press any key through the decimal keyboard, its equivalent 4-bit binary number is being generated, and these are being stored in the form of a 2 BCD number, in an 8-bit register or in a memory location. Now these numbers are called tagged BCD number. Even if the data is entered in the form of a decimal digit, it is inefficient to process the data in the BCD number, because in each 4-bit combination, we know that digit A to F remains unused. So whenever we are using decimal number, we used to use from 0 to 9, and A to F remains unused. So therefore, what is required? Each BCD number are normally converted into the binary number as far as the data processing is concerned. So the conversion of this BCD to binary number is an important perspective, and that is why we are going to write the program, how to write a program which is going to convert a BCD number into the binary number. So so normally whenever we take an example of the BCD number and which has to be converted into the binary number, for example, we have a 72 as a BCD number or the decimal number. 72 is normally represented as 7 into 10 plus 2. So the digit 7 represents 70 based on, because it is placed as a second position from the right. Therefore, converting 72 BCD into its binary equivalent, it requires multiplying the second digit by 10 and then adding with the first digit. So this is how we do it, not manually. So how we are going to convert 2-digit BCD into the binary number? So what we are going to do, we are going to separate an 8-bit tagged BCD number into 2 4-bit unpacked BCD digit, and it is designated as BCD1 and BCD2. And then convert each digit into its binary value according to its position. And then we are going to add both binary numbers to obtain the binary equivalent of BCD number. Meaning thereby, if 72 is given and it has to be converted into its binary, so what we are going to do, we have to fetch 2 and we have to fetch 7. We have to take 7 separate from 72 and we have to take 2 separate from 72. Once we obtain 7 and 2, because 7 is in the second position, so what we do, we multiply 7 by 10 and then we add 2 to get 72. So that is what has been explained into this. 7 is taken as BCD1 and BCD2 is taken as 2. And then after converting it into the binary, 7 is converted into binary, 2 is converted into its binary, and then BCD1 is being multiplied by 10. BCD1 is multiplied by 10 and then it is being added with 2, BCD2. So how it actually happens? Let us go with that example. Suppose we have to convert 72 BCD into its binary equivalent. So 72 is, this is 0, 1, 1 represents 7 and 2 represents 0, 0, 1, 0. That is why I have said whenever we press 2, it will be 0, 0, 1, 0. But when we press 7, it will be 0, 1, 1, 1. So what is the step number 1? This 72 BCD is a packed BCD. So this value which we are getting is the packed value. We have to unpack it, meaning thereby we have to unpack means we have to separate 0111 as well as 0010. So once we are going to separate, how we are going to do? First of all, this all bits becomes 0 and then we take 0010. So this is called unpacked BCD1. Similarly, this value is made 0, 0, 0, 0, 0, and this 011 is shifted right so that it will become 0, 0, 0 and 0, 1, 1. Now this represents 2 and this represents 7. So that will be packed BCD2, unpacked BCD2. So this is BCD1 and this is BCD2. Then what we do, we multiply BCD2 by 10. So that 7 into 10. And then after multiplying this value by 10, we will add BCD1 into this. So this multiplication, since we don't have any instruction by which we can multiply. So what we will do, we are going to add 7 10 times so that the result will be equal. And then after adding 7 10 times, we are going to add BCD1 into that. So let us discuss the flow chart for conversion. So first of all, what we do, we take the number, mask upper nibble, and store the number as BCD1. What does it mean? Mask upper nibble. This is upper nibble, this is lower nibble. This upper nibble is first masked. Masking means convert all these values as 0, 0, 0. So what that we can do the AND operation. So by doing AND operation, by what? ANDing with 0, 0, 0, 0 and 1, 1, 1, 1. What will happen? This will become 0 and this will become as it is 0, 0, 1, 0. So first of all, we are masking this nibble, upper nibble, and getting the result. Then in second case, masking this nibble and then rotate it 4 times right so that it will become this one. So that is what has been explained. So first of all, we have to mask the upper nibble and store the number as BCD1. And now take the number again and mask lower nibble and exchange the nibble position to result and store it as BCD2. And then multiply this BCD2 number which has been obtained by decimal 10 and add BCD1 and store the result and stop. So in this way, with the help of this flow chart, we can do it very easily. So let us discuss how it can be done. First of all, these nibbles has to be masked. So all this value should become 0. This value can become 0 if we do AND operation with 0, 0, 0, 0 and 1, 1, 1, 1. Means if I do A and I 0 F, this we will be obtaining. But whenever we have to obtain this, what we have to do? We have to mask this. So what we will doing? A and I F and then 0 so that it will become 0. All these 4 nibble will become 0. As well as after getting the result, we will shift it 4 times so that it will become 0, 2 and it will become 0, 7. When it will become 0, 2 and it will become 0, 7, this 0, 7 is multiplied by 10, means it is repetitively added 10 times so that it will become 70. And then we will add this 2 into that so that we will be getting 72. So in this way, we are going to do the conversion program from BCD to binary.